decision on what type of emulgent we need to select and what concentrations we need to add. If we are not having any particular surfactant of a particular HLB value, which is not suitable to us, then we are able to use as a mixture by calculating uh, individual HLB value of a surfactant and its contribution. How much is the fraction of its contribution in as an emergent? So we are going to take that fraction multiplied with individual HLB values. We need to add them so to get the total HLB value. So to use that particular one as an excipient according to this table wherever we want to use it. So because we are concentrating about emulsions, so we are taking the HLB value 3 to 6 for water in oil and 8 to 18 for oil in water, GPAT questions. So this is required to be known and you need to memorize. And now we are entering into a little bit very good concept and which is important also is preservation of emulsions. We know that emulsion is containing three components. One is the oil, and another one is water and emulgent. So we are preparing an emulsion because we are having a water insoluble drugs we are dissolving in the oil, so we can prepare them as a solutions and give them. But oils are bland in nature. That is the reason we cannot give them as such. We are preparing as an emulsion. Or sometimes we are having a water soluble components. We want to make it a little bit longer duration of action, and we want to have reduction in their bitter taste. So we want to entrap them in the water phase, and we are taking an oil outside. So this is actually water in oil emulsion we are preparing it. In all the cases, oil and water and emulgent, they are the very good medium for the bacterial growth. So these provide the microorganisms a good nutrients for them. Most of the times, these bacteria feed on non-ionic and ionic surfactants and some components like glycerin and emulsifying agents. So most of the times, the natural polysaccharide like Tetragacantha, acacia, these we are going to use them cause the deterioration of emulsion. Once the emulgent or the oil got broken or your water is contaminated or it is containing a growth of microorganisms, so that will affect the stability of whole emulsion. Most of the times the oil like arachis oil promote the growth of aspergillus and rhizopas. While the even paraffin, liquid paraffin, it is a mineral oil, it will also provide some of the species of bacteria like bursitis. In those cases, what will happen, we need to use some preservative to increase the stability of emulsion and enhance the shelf life. Otherwise, the emulsion will be degraded by the bacteria within a short span of time. So we need to add a preservative. But most of the times, these preservatives are necessitated because some of the contamination of emulsion could be not after the preparation, but it is during the preparation by the different factors. One is the contaminated emulgent, which is already present because it is a natural sources. They are collecting from different plants and gums. So there will be a contamination chances are very high. And deionized water, they are getting from the ion exchange resins, cation and anion exchange resins. So they are good medium to get entrapping these bacteria and grow. So we are going to get that as a contamination. Sometimes the equipment surfaces, they have got a crevices and gaskets. In those, bacteria will be growing and causing a contamination. And during storage, poorly stored closed container, in case of a multiple batches, we are taking from the same container or raw material. So the external environmental microbe will enter into the particular container. The chances are very high. So these are all the possibilities. So even though we can see that at most care, but during the stability also they will be growing. Even a small amount of microorganisms are present, they will grow to larger number, so they cause the damage. These emulsions are very much important and it will be given by all the routes. Whereas the parental route is given by, in the case of injection, we need to be sterile. So all the parental routes we are going to give in the form of an injection that will be entering into the systemic circulation into our body directly. So we need to make them sterile. not only parenterals, even that oral and topical, they need not be sterile, but we need to keep these microorganisms under the control because of the reasons what we have mentioned about the contamination from the different sources. We need to prevent the further growth. For that purpose, we need to add preservative. So the growth of microorganisms bring about certain undesirable changes. So the properties of emulsion getting affected. So the signs of instability, which include phase separation, that is the first thing which we are going to observe because the emulgent is getting spoiled. So phase will be separated. You will be getting one water phase and oil phase separated. Another one is the discoloration, because the emulgent got degraded and oil got degraded. So you are going to get a discoloration. A foul-smelling gas will be observed in the rancidity of the oils. So that causes the bad sense of taking a medicine, and it is not worth to take also. And changes in the rheological properties will also be there because of that reason. So we need to consider adding optimum concentration of preservative to stabilize your emulsion. But there are two major problems which we are going to encounter when you are adding a preservative. So what are the major problem and challenges which is adding a preservative to any emulsion is to get a adequate concentration in the aqueous phase is very tough. It is not easy to get the adequate concentration in the aqueous phase because most of our preservatives are oil soluble. They present in only oil. They will not present in the water. So the emulsions are heterogeneous systems due to the partition. The preservative tend to partition between the oil and aqueous phase. If it is oil soluble, it will entering into the oil phase only, and aqueous phase solubility is very less. So concentration is very less. So the microorganism will be start growing in the aqueous phase and attack the emulgent. So most of the time, the bacterial growth will be present in the aqueous phase. Even if you take the aqueous phase water solubility also, phase volume ratio, it is also going to affect your stability. Hence, if preservative is partitioned strongly in the oil phase, it is unless at the normal concentration, because at the low concentration remains in the water. So another one is the phase volume ratio is also we need to consider. When the preservative is more soluble in water, but its contribution is very less in the water when you are adding in water phase. So if you increase the oil phase to the water extent, to the greater extent, the proportion of the preservative in water is going to increase if you are adding total into the total value into the account. Because of this partitioning effect and the two-phasic systems, this will create a lot of problem in the concentration of the preservative in both the phases and creating that optimum concentration where it can kill the bacteria. That is very tough. Now, the second problem is you are able to add sufficiently larger quantities of your one if they are provided not toxic, but the preservative should be present in unionized state. Unionized state means it should be having a not divided into ions to get entering into the crossing the bacterial cell wall. If ionized species of a preservative, they will not enter into the bacteria by the barrier effect of a bacterial cell wall. So as to penetrate the bacterial membrane, we need to have an unionized species. But unionized species will not have a solubility in water because it is a polar in nature. So you cannot create a greater concentration, even though it is present in the water, we are able to do it. They are present in the ionized state in the water, so it will not attack the bacteria. Again, the bacteria will grow. So the activity of the weak acid, for example, like benzoic acid, if you are having as a preservative, they decreases the when preservative action will be decreasing when the pH is increasing, because at the higher pH level, the weak acid will become as a salt and it will be present as an ion. Say you are adding a sodium hydroxide, increasing the pH, it will become a sodium benzoate, CO minus and A plus. So the ionic species are formed. So the preservative action will be less. It means even though you are adding sufficient concentration and you are able to make them in the present in available in the water also not sufficient, we need to keep them in the unionized state. This is actually what the problem is. Most of the times in the unionized state, water solubility will be less. It will get precipitated. So we need to make a solubilized at the same time anionized form to have a effective. This is a second challenge. So the preservative must be free and not to bound to the any another components of the preservative. Most of the times, if you see the phenols, they will be having interaction with the oxyethylene groups of your polysorbate that will be causing a reduction in the phenol concentration in the product. It will increase the bacterial growth. So it should not interact. It should not have any interaction with another excipients. Then also the concentration will be less. The pH should be optimum and it should be present in the anionized state and concentration need to be perfect. Then only the preservative action of a any antibacterial agent which we are adding, so that will be given to the stability of emulsion. This test you might have done in the microbiology lab, preservative action of any antibacterial agent. If you did not do it in biotechnology in the 4th year, you are going to test it because the product which you are doing, so you need to microbiologically test that whether my product preservative is having a reduction in the bacterial growth or not. Most of the times we need to see the requirement of the preservative agent before we are adding into the emulsion, because the agent should be non-toxic and it should be non-irritating, and non-toxic means it will not causing any damage to the patient, and it should not have even applying onto the skin or taking into the oral cavity. It should not cause the irritation and it should not have corrosion in nature. So if you use a phenol, it is corrosive in nature. It causes the irritation when its concentration is a little bit high. It should be bactericidal when compared to bacteriostatic. This is another requirement. Bactericidal means it will kill the bacteria. Bacteriostatic means it will prevent the growth of the bacteria. It will not kill. If bacteria is not killed and it is still alive, but the growth is prevented, a time will come it will start growing. So we need to select a preservative. It is having a bactericidal action. And the action needs to be very rapid in nature. Before it is multiplication, it should act, and it should be broad spectrum, like it will be acting in bacteria, fungi, and gram negative and gram positive also. And if the preservative it should not be getting affected by the microorganisms. So we are using the preservative to kill the microorganisms. Some microorganisms have the capacity to degrade the preservatives also. Say for example, Pseudomonas group of originose that can attack the phenols. It makes the product not suitable to use. So act even in the larger number of the bacteria, even if the concentration is very high also in unpredictably if it is more, it should be able to reduce their growth and kill them. So this is actually what we are going to have, the optimum qualities. So the efficiency of the particular preservative influence also influenced by the emulsion type, whether it is oil in water or water in oil, whether it is a micro emulsion or multiple emulsion, and the nutritive value of the product, whether it is having a good nutritive value, the growth will be very high, and the degree of aeration that will encourage the growth. In the case of aerobic bacteria, supply of oxygen, and the type of the container used, whether it is completely closed or for the repeated doses you are making it open to atmosphere. So such things we need to consider to have a preservative action, whether it is working or not in our emulsion to enhance the stability. The examples of the preservative, most of the times which will be used depending upon the purpose what we are going to use. So the sodium benzoate, food preservative, para-amino benzoic acid, sorbic acid, chlorocresol, and chlorophenol, mercurial soaps, they are used for the topical preparations, and salicylic acid. Such preservatives are generally used to make our product stable. So now you have got HLB value, how to enhance the stability. We have added the preservative, and we are going to see that my emulsion is stable or not. So this can be seen by physically also, by seeing a creaming and cracking and agglomeration, such things. We need to see the rheology of the emulsion also. So that is the reason. Another question you are going to have, one is a HLB value and how to take this HLB value system to select emulgent and prepare emulsion. The second one is how the preservative is getting selected and enhance the stability, and how to enhance the preservative action. The third question is rheological properties of emulsion, to see that whether that emulsion is stable or not, how it is behaving. So this is the another third question you are going to be expected in emulsion portion of force dispersions, what we did not touch previously. Why did not take this one is rheological properties are you already got studied in the first session in the rheology chapter. So the same concepts which will be applicable here also. The reason is that the rheology what you have learnt in the Newtonian and non-Newtonian flow, if I am teaching them and I am asking them to use your viscometer, Ostwald or cup and bob or it is a cone and plate, you will not be able to understand. But you can write the same answers here also. What are the equipment used to study the rheological properties of emulsion? You know the same answer, you can write it here also. But you need to understand what the flow the emulsion is exhibiting, that you need to know it. So for that purpose, we need to have an understanding of this particular concept. So the following are the flow-related attributes are desirable for the overall performance of emulsion. Most of the times, this is very much important when you remove the bottle. By using a bottle, we want to take some dose. So removal of the emulsion particular dose volume from the bottle or a tube. If it is a cream, it is also emulsion, it is present in the tube. So we are able to remove it or not, whether it is having optimum viscosity or not. So the viscosity of the container, the emulsion which is present in the container is able to make the removal easy or not. So that we need to consider. For that purpose, we need to study the rheology. There is no other option. We cannot say that I am taking it and not at all coming it is. So how can you know that what is its value of a rheologic impact where you are present and what type of flow that is. So we need to study this one by using an equipment. So the flow of emulsion through the hypodermic needle, that is another important when you are giving in form of an injection. Otherwise, the needle will get choked and you will not be going to have a proper emulsion. And during the transfer itself, the globule may be losing its emulgent effect and they are breaking before entering into the bloodstream. Another one is the spreadability of emulsion on the skin when you are applying it, how much extent it is spreading over it. So based on that, we will be having a viscosity and we are having the rheology is impacting on to the spreadability. Stress-induced flow changes that during the manufacture. Most of the times you may be already learnt in the rheology. You are having two types of the flow. One is Newtonian, another one is non-Newtonian flow. So you have got a Newtonian flow where you have got your shear stress and velocity gradient both are having, when you are plotting it, they have got a linear effect, so you are getting a straight line. Whereas in the non-Newtonian liquid, your velocity gradient and the shear stress, they are not linear. They are having a curvilinear relationship. So you are getting divided into the two types. One is dilatant flow, another one is the plastic flow. Plastic flow again divided into the two types. One is a pseudo-plastic flow and a plug flow. In the plug flow, there is one point is that yield point is there. You need to apply the yield stress beyond that particular yield point, then you will get a velocity gradient. Otherwise, you won't have the flow. So that plug flow, it has got its own requirement of a certain optimum force we need to apply to make it thinner. So once the flow is applied, this will be acting as a shear thinning system, and we are going to have the same thing which will be used same as that of your pseudoplastic flow. In the pseudoplastic flow, you don't have yield value, that is starting from the origin. So you don't require any extra force. So this is the concept when you are applying it in this particular case where it is behaving like a dilatant or it is a shear thinning or it is a shear thickening like dilatant flow. You will be able to know that will affect your manufacturing equipment and you are going to select whether it is a Sigma blade blender, you want to use any semi-solid equipment. So whether it is a shear thinning and shear thickening system, most of the times in the pastes, you are going to have this impact of high solid content. You are going to have a dilatant flow. So such things will be decided what type of equipment and how much energy is reused. That can be calculated by using these rheological properties. Now, considering them, we are going to have the rheology of emulsion as mainly similar features as that of the suspension, but there are certain deviations which are present when compared to your suspension, what you have already learnt there. So the rheological equipment applied there also, here also, but we are going to have a specificity here with respect to rheology because the liquid-liquid interface that contains surfactant or a polymer layer introduces a response to deformation, and one has to consider the interfacial rheology when compared to regular and all our individual continuous phase and dispersed phase, because it is a two-phase system where we have got a third one is very much critical, which is interface. That is going to impact your rheology. Remaining are two liquids, whether it is one it is oil and the another one is water. Both are having certain viscosities, but when you are making an emulsion by adding an emulgent, it will have a higher viscosity, and because of its interface, that is having going to interfere with your rheological properties. So the dispersed phase viscosity relative to that of the medium has an impact onto the rheology of emulsions we need to consider. And in the previous case, what we have seen in the suspension is solid content, percent solid content, and its behavior of the solid content, that is the density and size of the particular solid, which is going to give an impact. So here the dispersed phase viscosity, what we are going to view is having an impact. And the deformable nature of the dispersed phase, because the globules which are having maybe a flexible, or we are making a some sort of cross-linking, you are making them harder, they cause the variations in the emulsion rheology, flow properties. So we need to study them because of these variations for the emulsion. Most of the times we are thinking to do the accelerated stability testing, what we have already seen, we cannot increase the temperature, so we are doing a centrifugal force. So the centrifuge we are going to use the study the rotations under the RPM at certain time, and we are taking the rheology of the particular emulsion. If the starting rheological properties and the upper centrifuge also, both rheology is pattern is same, graph is superimposing, then the emulsion is stable. In general, dilute emulsion exhibits the Newtonian flow. It means it is behaving as what you have got as solutions and common solvents which we have got used, and in the first semester you have used Ostwald viscometer that can be used to study these dilute emulsions, especially your micro emulsions and the dilute emulsions. You can use the simple Ostwald viscometer, and the construction working you know it, and you have studied in the rheology, that is applicable. Here also you need to use them, but it is applicable to the dilute emulsions only. As the viscosity of the emulsion increases, flocculation of the globule will be reduced. It is having a scaffolding effect, and you will be having a particular period of the time it is untouched, it may be having a creaming, just like you are having a hard cake. In the case of suspension, you may be having a cream. At the same time, if your viscosity you are increasing to too much extent to prevent your flocculation, but you cannot remove the emulsion from the bottle because the consistency is difficult to pour. It will become very thick. That is not good. So it is a contradictory principle. If you want to increase the stability by enhancing the viscosity, viscosity will not allow you to transfer your material from the bottle. So you need to select the optimum viscosity for the desirable nature and pourability and good stability. So for that purpose, during your manufacturing also you are studying the rheological properties, and you are seeing that how they are behaving, whether it is Newtonian and non-Newtonian. Most of the times, the concentrated emulsions, like coarse emulsions, what we are going to take it, and multiple emulsions, they exhibit non-Newtonian flow. Their behavior of a shear stress and velocity gradient is not linear. Most of the times, in the lower level of your emulsions, not having a semi-solid in nature, they will be having a pseudoplastic flow. There we need to use multi-point viscometers. Whereas in the creams, we are going to have these multi-point viscometers to determine the yield values also, and they used for the viscosity analysis. So you already learnt in the rheology some of the viscometers like a cup and bob, and you have got a cone and plate viscometers. So these are all multi-point viscometers where you can change your shear stress to have an impact onto your velocity gradient. So you can study it, how they are behaving. In the case of Newtonian liquids, Ostwald viscometer, you cannot change the shear. Only gravity is getting affected, so it is flowing through a micro board, that is capillary tube, and it is taking how much is the time you are calculating it. But in the multi-point viscometers, you can change the RPM of the probes. Then you can have the impact. on the velocity gradient, you can find whether they are shear thinning system or shear thickening systems. It means they are pseudoplastic or dilatant flow. You can determine by using those equipments. These are all the rheological properties we need to consider in the emulsion manufacture. Next, we are going to see emulsion stability. This is the third question you are going to have after your HLB value, preservation, and you have got the rheological properties, and you are having emulsion stability. What are the major factors that will affect your emulsion stability? You are going to get as a 5 marks question generally. 2 to 3 questions, they merge it together to get a 10 marks question in the exam. And the factors you need to list in the 2 marks question you are going to have in the exam. And GPAT, of course, you have got all the concepts need to be clear. So what is the emulsion stability, how it is getting affected? So the stability of the emulsion is the most important aspect of the preparation of emulsion when we are going to prepare in the manufacturing state and storage and distribution state. This is characterized by the absence of coalescence, that is no internal globules are coming together, and creaming, they are separating as a layer, and maintenance of the elegance, good looking without changing in the color. As regards to the appearance, color, order, and other physical properties. What it is having a transferability. So these are all things we need to check. But the first sign of instability is the breaking or cracking of emulsion. That is the worst case problem in case of emulsion. We need to throw it. There is no other option, and we cannot make redispersed again when this phenomena has occurred already in the stability. This is the reason. This is worst case scenario of a suspension, that is emulsion stability. This is coalescence of the dispersed globule and separation of the dispersed phase, which is not reversed by the shaking. This is actually worst phenomena. And you may get the question, what factors that affect this so that I can prevent it? And during my storage and manufacturing, so that I can avoid this worst case scenario. So any chemical or a physical or biological effect that changes the nature of emulgent that makes less stable and cause this cracking. So what are the changes? This is very important for your exam. What do you do the prevention of cracking and breaking of emulsion in the enhancement of stability? So you want to have a shelf life of longer duration. So you don't have any accelerated stability testing like increasing the temperature. You are using a centrifuge and agitation for the emulsions to see whether the breaking is taking place or not. So you are going to have these factors of 3 chemical and physical and biological effects of these emulgents that will make the cracking we need to study. The first point we need to consider is addition of emulsifying agent of opposite type. What is this phenomena? How it is going to cause the cracking and breaking of an emulsion? So don't use opposite type of emulsion to prepare a particular type of emulsion. Say for example, monovalent metal ions, that is sodium salts of your stearic acid and potassium salts of stearic acid, they are having a monovalency. Most of the times they are having oil in water emulsions because sodium stearate and potassium stearate, they are having water soluble in nature. According to rule of Bancroft, we have already seen wherever the emulgent is soluble, that will become a continuous phase. So monovalent metal soaps are water soluble, so you are going to get oil in water emulsion. But the same stearic acid, it is reacting with the divalent cations like calcium and magnesium and zinc. So they are going to have the soaps that are forming oil in water emulsion. It means that when you are taking these emulsions and adding some calcium salts as a drug or as an excipient to the monovalent cations, it will precipitate and it will crack the emulsion. So adding one to the other leads to the instability. Also, anionic and cationic surfactants are mutually incompatible. We should not have a mixing of them, and it will cause the emulsion cracking. So an oil in water with sodium stearate can be converted into water in oil by adding a calcium salt to it, and because it will form the calcium stearate. The calcium stearate is more soluble in oil, so according to the rule of Bancroft, oil will become a continuous phase. So when it is oil, it become a continuous phase. Oil in water will become water in oil emulsion. So this is actually, it is very problematic because sometimes we need to add a electrolyte. So these electrolytes are added to make your emulsion isotonic with your blood in case of whatever we are going to use in the parental suspension. So we are going to have. So in those cases, this type of problem will come. The second is decomposition or precipitation of emulsifying agent. This is caused by the salting of the effect. Say for example, you have got alkali soaps, whether it is a sodium or potassium or calcium, anything. If you are adding a sodium chloride to it, so we know the zeta potential. So the concept of repulsion and the attraction, we know it. So when you are adding more salts, the sodium chloride, it will be making a salting out effect of that emulgent. It will cause the removal of emulgent, and the precipitation of emulgent cause the emulsion to crack. So anionic and cationic emulsions are incompatible, we have already seen, and when they are added, then it will also be cracked. Non-ionic disinfectants are incompatible with phenol, so both we should not add, and making most of the times we are going to have the surface active agent itself, it will be having some action in the preservative, like a cetrimide, anything. So such actions will also be required to be seen. Gums, gelatin, casein, they are insoluble in alcohol, leading to the cracking if you are adding alcohol as a preservative. So because the preservatives are insoluble, so they will be getting precipitated, and you will get a precipitate and cracking of an emulsion. The third one is addition of the common solvent. So you are adding a solvent that is solubilizing both the dispersed phase and your continuous phase. Say for example, you are adding alcohol to castor oil emulsion. So it is containing castor oil, soft soap and water, all are soluble in ethanol, so it will get cracking, will be taking place. This is actually another problem we are going to have, and decreases the stability. Another one is microbial action. We have already seen for that purpose only we have studied the preservative action of your antimicrobial agents. Most of the times the molds and bacterial might destroy the emulsifier, leading to the cracking. Therefore, the emulsions are recommended to have a preservative, and that preservative also having a sufficient concentration and non-ionic in nature, and it should not have interaction with anything. So to be stored in a longer period of the time. Most of the times our emulsions we use it to be dispensed in the ancestors dispensing pharmacy for 1 week. There without adding a preservative, no problem. But we are not doing a week preparation and giving to the patient now. We are giving preparation and kept in the pharmacy store for 2 years like that, and we need to sell them. So we are not manufacturing ready-made. Because of that reason, we need to add a preservative to be stored for a longer period of the time. The fifth factor that will cause the cracking and breaking is excess of a dispersal phase. What is the excess of dispersal phase? So the alteration of the phase volume ratio also causes the inversion of an emulsion. So that will be having an impact after you are making a manufacturing of emulsion. If you are doing it, it will cause a breaking. If you are doing as a part of manufacture, it will enhance the stability. So say for example, mixing an oil in water emulsifier with oil. So oil is present in the dispersal phase, and again you are mixing with the oil and adding a small amount of the water. So you are having a dispersal phase added, and more dispersal phase when you are adding it, then what will happen? That phase volume of that particular dispersal phase is very high. So whenever you are making an emulsion, you need to remember that you can add dispersed phase up to 74% of your emulsion. Beyond that, if you are adding your dispersed phase, it will become breaking, because all the emulsion globules are present in a spherical space and spherical in nature and the shape. So the void space, which is accounting 26%. So beyond that, if you are adding the dispersed phase, that dispersed phase will become a continuous phase. And if you are doing the same thing after preparation of your emulsion, to add something feel effect, or you want to have a dilution effect, and you are adding that, so already phase volume ratio is very high and it will break. This is applicable to your water in oil emulsion also. So the addition of the more water gradually reaches the inversion point, and oil globules are developed by the water to form the oil in water in the case of water in oil emulsion if we are adding more water. This is employed in the continental method when you are doing phase inversion as a approach to enhance the stability. So the emulsions are phase volume concentration. When you have a dispersed phase concentration, phase volume ratio exceeding 74% have a marked tendency to crack. So we need to see this. Because if a given space it is filled with closely packed small spheres of uniform diameter, they will occupy 70% of volume irrespective of their size. Whether it is smaller in micron or nano or it is in the mm level, so they will be having maximum of 74% only, it will be dispersed. Beyond that, you cannot disperse. This is very much important and critical in the GPAT also. Another one is higher temperature. This is the reason we cannot employ emulsions accelerated stability testing. Because of all these interconnection of these problems, I did not teach you this particular portion during your first session. Because you have already seen that accelerated stability testing or stress testing you cannot do for the emulsions, because when you are increasing the temperature, within minutes it will crack. The reason is the changes in the emulgent behavior and disruption of the emulgent layer, it will have a drastic effect which is not present in regular room temperature. And you are declaring that it is unstable. That is the reason we are creating a stress conditions by using centrifuge and agitation. So temperature increases the number of molecular collisions which cause the cracking, because the more globules are moving very fast and they get a coalescence and that will become further spreading, creaming, then it will become a cracking. Also it causes the coagulation of monomolecular emulsifiers, that is the proteins, and most of the times freezing on the other hand produces the crystals of the aqueous phase, that crystals having a little bit value more than your liquid, because the crystal is having a solid in nature. Solids are having lighter in nature when compared to your liquid, so that will break the emulsifier, and the salt concentrate in the remaining unfrozen part, so you are going to have the breaking of emulsion. An emulsion prepared by the heating and mixing the two phases can invert the on the cooling, probably due to the temperature dependence of the solubility. It will happen if you have got a higher temperature, it is oil soluble; in lower temperature, it is water soluble, or vice versa. If you are increasing the temperature, so the emulsifier behavior will change and the emulsion will be formed, will be reversed. That is phase inversion. It will cause the instability. Most of the times we cannot keep emulsion in the freezer or a refrigerator. The reason is that will cause a changes in your densities differences. If it is frozen, only water will freeze and oil will not freeze. So if water is a continuous phase and you are having the oil as a dispersed phase, after freezing it, the oil will be getting shrinked and emulgent layer is disrupted. Similarly, when it is a oil is a continuous phase and water is a dispersed phase, there also water will be getting expanded when it is becoming a solid, so it will break the emulgent layer. Because of that reason, this temperature effect, we cannot store the emulsion at a higher temperature also, deep freezer also, that is in the refrigerator also. We need to keep them in the room temperature only and study their stability only by using agitation and centrifugation. The second approach, what you have got a problem, you already know it in the first year itself, you might have studied creaming. It is caused by the gravity. Most of the time type of emulsion it will decide whether it is upward or downward creaming on the density of the dispersed phase and continuous phase. Oil in water emulsions cream upward most of the times because oil globules are lighter in nature, while water in oil emulsion they cream downwards because water is heavier than the oil, that is denser than the, so oil is less than the water, so they tend to float in the case of oil in water emulsion. So the dispersed globules retain their identity, do not coalesce on in the cracking, and shaking reobtains into a uniform redispersion. That is the reason this creaming is not that much dangerous when compared to your cracking or breaking. So this is not as serious as a breaking, but unless otherwise it is redistributed properly. But it causes the inelegance because and separate layer is present and it will not look nice, and inaccurate dosage because oil is containing a drug, so that may be present more portion in your dispensing spoon. So this is likelihood of coalescence is also present. That is the reason we need to avoid it. How to know this, whether it is having, we need to apply the Stokes law. This is GPAT question. V is equal to D square, rho 1, that is whether it is a density 1 of solvent, one solvent, that is, and the density 2 multiplied with the acceleration due to gravity divided by 18 eta. So for that purpose, we are reducing the particle size to decrease the D, or increasing the viscosity to make it more in the denominator. So we are reducing the stability. We are going to have a stability. So decreasing the D, it will cause a smaller size and the velocity will be reduced. Whereas increasing the eta, it will reduce the falling. So you are enhancing the stability. So thus to control the creaming, we can utilize these factors. Reduce the mean size of the globule size, efficient homogenizer, and increase the viscosity of the continuous phase, whether it is thickening agent used for whatever the continuous phase. Generally, methyl cellulose is used for water in oil emulsion, and soft paraffin is used for the water in oil, and this is oil in water emulsion. This is reverse, so you need to have, and we need to store this. We are going to have, because methyl cellulose is soluble in water at the continuous phase, if you are going to produce oil in water emulsion, and you are going to have a soft paraffin in water in oil emulsion. You need to store in a cool place. Decrease the temperature reduces to the viscosity and the number of collisions between the globules, which are going to reduce its creaming, but you need to avoid the freeze. In the cool place means we should not expose to the direct sunlight, such things we need to take care. The third phenomenon of stability problem is flocculation and coagulation, that you already know it. Globules are aggregate into masses of the emulsion, but do not coalesce, may be redispersed on the shaking, and if it is left uncontrolled, they may cause the cracking. So we need to consider this also into the account. The fourth one is the phase inversion. This is the critical phenomena. We have already seen. One is adding the opposite phase, changing the monovalent to the divalent, or we are increasing the temperature, changing the temperature changes, which causes the phase inversion. So in all the cases which we are going to have a cracking as the problem. But when you are doing the same phenomena of phase inversion during the manufacturing itself, intentionally you are phase inverting it, the emulsion will be more stable. That we need to employ, not during your storage, but during your manufacture. Phase inversion will cause a beneficial effect. So if you know this particular phenomena, which is already your length, just you need to understand two concepts which you need to abreast again is what is difference between the multiple emulsion and micro emulsion. This is the one we need to see. Multiple emulsion and micro emulsion. So you know that you will be asked 2 marks question, define them and differentiate them in the 5 marks question, and making manufacturing. So in the 5 marks question, you are going to expect it. Micro emulsions are, you already seen in the coarse dispersion, nano dispersions, that is colloidal dispersions. We have already seen them. Then again, we are making it little bit seen. Micro emulsions are monodispersed spherical droplets which are having a size lesser than the 100 nanometers. Most of the times, water in oil or oil in water, which you are going to present. Only the difference between the coarse dispersion and this dispersion is it is having a globule size less, because it is having a presence of surfactants and co-surfactants. Most of the times, if you see in the diagram, they are appearing as good as your solutions. So the micro emulsion, they appear as a solution. They will be having a Newtonian flow, and they are very much stable than regular coarse emulsions, because they are containing one additional component in addition to your oil, surfactant, water. They are containing a co-surfactant, because when you are adding a surfactant alone, its concentration in the emulsion will be very high. Because of that reason, you will be having giving a toxic effect to the patient. So to reduce the surfactant concentration, you need to decrease the concentration of the surfactant, but it will not produce microemulsion. In those cases, you need to add a co-surfactant that is not actually a surfactant. It enhances the surface active agent capacity of original one what you have used. So in the combination, we are going to use. Here you know that what is the combined HLB value, what we have already seen previously. by taking each fraction and individual HLB values of both, you can add together surfactant, co-surfactant, what is the total HLB value, and we can see that whether it is fitting to our emulsion or not. This we need to consider. It means in the micro emulsion, what is the major difference between this and this in the composition is co-surfactant is present in the case of micro emulsion. It is not present in the emulsion, regular emulsions. We are going to use only one. Most of the times, micro emulsion is used as a good vehicle to have a unique solubilization properties, and also it is having a potential drug delivery system to entrap your oil-soluble drug moiety entrapped in the micro droplets and enhances the surface area and encourages the bioavailability in case of poorly permeable drugs like curcumin, valsartan, and glyceride. In this particular case, you are having a poor permeability and poor water solubility is very less. In those cases, it will help. The second concept is multiple emulsion. In the multiple emulsion, you have got a emulsion of emulsions. First, you prepare emulsion, and again you do the second step emulsions to make an emulsion of emulsion. So, if you want to make this as a solid globule, then you are going to have a third step called as a cross-linking and converting them into solid globules. That is actually microcapsules preparation that you are going to learn a little bit later. But this concept is very much required there to be utilized. So multiple emulsions are the emulsions of emulsions in which droplets of the dispersed phase themselves contain smaller dispersed globules present in them. So there are two types of multiple emulsion. One is oil in water in oil. Another one is water in oil in water. So O by W by O, W by O by W. So they are having an increasing interest because they have got a sustained release, prolongation of action, and it has got a taste masking effect. It has got increased stability. So we are going to have them as a delivery system. So it is also having unstabilized drug which can be stabilized by the encapsulation by using a cross-linking, and we are converting the globule into a solid and dispersing them as good as your regular suspensions, which is having more stable. Suspensions are more stable than your emulsion. So the coexistence of the two immiscible agents in the same preparation, you can entrap two drug molecules in two phases, what we are going to use. That is another advantage. So two drug molecules you cannot mix. If you prepare as a common tablet in the combination therapy, so you want to separate them, you can disperse them in the one globule and another globule. So you are going to have a separation with the intermittent phase also. So you are going to have a better stability. Most of the times, emulsion stability, emulsion method, manufacturing method. So it is a two-step process. So what will happen? You are going to have a drug solution and the oil phase containing the emulsion stabilizers are combined to get the oil and water emulsion. So this will behave as the oil in the step one, and you are using this oil in water, water in oil emulsion as a dispersal phase in the second stage. So later you are going to make this one and disperse it in the polymer solution which is containing the water. So this is the way you can make your multiple emulsion. In the another way, preparation of the primary emulsion, oil in water. So water is your continuous phase now, but you are using this as a water as a dispersal phase in the next stage, and you are going to disperse in the oil, and you are going to get the oil as the outer phase in the steps two. So you are going to get oil in water in oil emulsion. So this is the way you can prepare these emulsions. So it's two-step process. First, primary emulsion, the oil in water, then you are converting into oil in water, dispersed in the again oil. So you are going to get a emulsion multiple. So you can have water in oil, again you can disperse it in the water in oil, again in the water. So the second type of emulsion you can make. So you have already seen now the concept of both, and we are preparing them in our pharmacy because they are having an extraordinary stability when compared to your regular solutions, which are having a taste masking power. That is the reason we are going to sense them, not sensed by the taste buds, because it is getting entrapped with some of the moieties. Like your continuous phase, you have got a adding any flavor which is more palatable, then it is going to be good. But at the same time, we are going to have an advantage of giving a oil, water soluble, water insoluble material in the case of emulsion dispersed in the oil phase, and we can give them. This is actually what the advantages we are going to gain. So with this, we are having to some extent to an end for the coverage of our portion. In this particular case of emulsion, what we did not dealt, you are going to have a 4 type of questions. One is, how do you prepare emulsion by using HLB system? One, how do you preserve the emulsion? How to select a proper preservative? That is the second. Rheological properties of emulsion. That is third. Stability of emulsion, how you enhance the stability. There are different problems of stability, creaming, that is cracking and creaming and coalescence and phase inversion. So how to avoid them? So you are going to get. But in you are going to have, what is the multiple emulsion? How do you prepare it? This is another question you are going to have. And one more question is micro emulsion and how do you prepare it? Most of the times you have already seen in the colloidal dispersions your SNETs and SMETs. So that is actually self micro emulsifying system and self nano emulsifying system. In the colloidal system you already learned. So we are going to use emulsion with high concentration of surfactants. We are going to use them in the preparation of emulsions like micro emulsions. So we are going to use 2 component surfactant. So we are going to draw a ternary diagram. So in the ternary diagram, at what concentration of these 2 combinations, when you are doing it, you are going to have a greater effect of your spontaneous conversion into emulsion we are going to study. So that is actually manufacture what we have already explained in the colloidal dispersions in the preparation of micro emulsion. I did not take them. I taught here only preparation of multiple emulsion only. In the filter preparation of the micro emulsion, what you require to do, first you need to study in which oil your drug is soluble. That is the first step. You select whether it is a linseed oil, arachis oil, or it is any oil, coconut oil of better stability, which you are going to select to dissolve your drug. First you dissolved it. And you need to select what is the surfactant concentration which is producing a spontaneous emulsification by using a ternary phase diagram. So we are going to draw amount of oil, amount of water, and amount of surfactant. So this is we are going to take it. Before that, we are going to select emulgent concentration, that is surfactant and co-surfactant oil mix. That is both all the 3 which you are going to make it. So we are going to get a region of emulsion region, nano emulsion region, and micro emulsion region. We are going to select and fix the concentration of co-surfactant and surfactant and oil. After that, we are making that into a solid or a semi-solid, giving in a capsule. When you are adding it to the water simultaneously and spontaneously without using your trituration or mortar, it will become emulsion. So that you are going to produce as a micro emulsion in situ. This is an excellent. It means you are giving emulsion as a capsule in a semi-solid form when it is reacting with the water in the stomach, and it will be forming as a micro emulsion within the stomach. That is called as a self micro emulsifying systems or self nano emulsifying systems. They are having a greater advantage.